Thanks for our talk. Yes, I'm James. This is Manny, my colleague over here, Cognizant, both data consultants in the data science and engineering space. I'm going to talk to you today about some work we're doing with one of our clients, where we've been applying agent-based models to run simulations on using EKS. So I'm going to talk about the problem that we're solving for the client and introduce the concept of agent-based models. And I'll hand over to Manny, who's going to talk about how we can roll this all out to production. So, first things first, the problem. We are working with a client that has a requirement to train a number of our employees. And they have issues with long-term planning of these training schedules. So we've been brought in to help, using some of their data, help optimize both the number of trainings that are making their way through the pipeline and the rate at which they're going through. So what I've got up here is a typical example of what one of their pipelines look like on the right-hand side. So you can see that it can get quite complicated. So everything on the two grey boxes on the left-hand side represent trainees entering the pipeline. The blue boxes, they represent each of the individual courses that they might take. And then the yellow diamonds, they are points at which they can take a different branch down the training pipeline. And then finally, you see on the right-hand side, you have a number of grey boxes that represent all the different qualifications that people come out. So there's a kind of funneling effect where everyone kind of comes into one course and they spread out, a bit like the university courses that you might have done. So some of the challenges that are facing here around how long it takes people to get through. They have to schedule all of these courses, they have to arrange classrooms, they have to arrange trainers. So it can be challenging to make sure that the right people are in the right place at the right time. And one of the things that can happen is if you wind up with some bottleneck. If 20 people are in the course, and the subsequent course only has 10 spaces left and it only runs every so many months, you're going to end up building a bunch of people waiting to join that course. Also, they have a problem with attrition, so a lot of people will decide to leave those courses. So we want to be able to dig into the flow of the people through the courses to understand why they're leaving. Is it because they're waiting around too long? Is it because the course isn't very fun, etc.? So, how do we go about doing this? We wanted to use agent-based models. I don't know if anyone heard of those. There's various different applications for them. But essentially, what you have is you have a simulation tool where you have agents that represent real-world actors. So in our case, that would be individuals participating in the training program, navigating through. And they are designed to mimic the real actions that those individuals would take. So the key point is that the agents themselves, they can act independently based on the rules and logics that have been set up. For instance, a trainee might make independent decisions on which courses to take based on possible options or their personal circumstances. The decisions happen in isolation, but they are influenced by the various course attributes like how long the course takes and how available the course is. So even though the agents are independent, they are constantly interacting with the other agents in the system as well as their environment. And this interaction is really crucial because it's through this that the complex behaviors emerge. For example, in our model, a trainee might experience delays if a course is full, which can lead to indirect interactions with other agents when they're competing for a slot on a subsequent course. And another kind of key thing that happens with ABMs is that the kind of system behavior as a whole emerges from all of these simple agents interacting with it. So in simple terms, each agent acts on its own, but all the overall outcomes, like the pipeline bottlenecks we talked about, or understanding and optimized training routes through that, they're resolved with agents' interactions within the system. So this emergent behavior allows you to uncover the insights and help you with your decision making, etc. So a couple of case studies. Like I said, there's a number of different applications for ABMs. The one on the left here is around trying to model what would happen if suddenly everyone plugs in an electric car after they finish work. How's the electricity grid going to cope with that? So you can use these kind of things for that, as well as the other example being modeling the COVID-19 pandemic interventions and seeing, like, if you tell them to isolate for 10 days rather than 7, what impact does that have? But there's a whole number of applications that you can use them for. For example, supply chains or traffic management or something like that. Basically anything where you've got flow of something from one end to another and even feeding back into itself is a candidate for using AVMs. So I have done a nice little diagram here to just kind of illustrate the kind of complexities that can emerge when using an AVM to model something. So I tried to mimic a really simplified situation that we've been modeling. So in this case, we've got 3 courses, course 1, 2, and 3. And you can see at the moment, course 1, it's got a capacity of 10, and there's 10 people in there. And we've got a nice little blue friend at the top there waiting to join the course. And he's waiting, he has to wait 1 month for the course to finish. On the right-hand side, I'm kind of flagging up all of the inputs and outputs that are going to arise as we step through the model. So in this case, we've got capacity and duration of the course, and then we've also got how long our little blue friend is waiting. So if we step through, we can see a typical thing that may happen. We hit this streaming point, a different branch down the pipeline, like I showed at the start, and 40% of the people are joining course 2, and 60% are going down to course 3. And our little blue friend can begin our course. And you can see that the inputs are starting to expand. So we have capacity and duration for the second and third course, as well as the ratio that they are moving down the different branches. And our outputs start to grow as well. So we have how long people are taking to complete the course and also the numbers. And if we step through one more time, we can see that a bunch of people could graduate, a bunch of people could drop out of the course, whether it's they fail or they decide it's not for them. And our little blue friend is able to carry them through. And you can see that the number of inputs and outputs grow quite quickly. And this is quite a simple example. We haven't included things like demographics of the people who are taking these courses or like their performance within the courses, etc. If you start to kind of try to model all of that, then you suddenly get an explosion of inputs and outputs, which makes it quite challenging. So I've just drawn them up here. On the left-hand side, we've got our inputs that we've shown there, and essentially each combination of values that you enter into those inputs, that represents a permutation of the model. So you can run as many permutations as you want and start to see what would happen if we bump the capacity on course 1, how would that impact the rest of the flow. And that's all done by analyzing the outputs that you get from there. So agent-based models, they're a powerful tool for simulating these types of flows. But they do come with their own set of challenges. So they can be complex to set up. Building an AVM requires quite careful design. We need to model not just the agents themselves, but also their interactions and all the rules that govern those interactions. So this often comes around by building detailed scenarios, and it can take quite a lot of time to set up correctly. You also need a lot of domain knowledge. So in our case, we need to really intimately understand all of the courses and how they interact with each other and the types of people who are taking them. Another thing that can happen is the computational cost. As the networks grow quite large, we saw that the kind of inputs and outputs can grow quite a lot. And if there's lots of steps, lots of different paths, you have lots of agents that are going through them, then it can take quite a long time to run the simulations. And Manny's going to kind of touch on that in a second. And finally, interpreting the results can be quite tricky as well. And that kind of feeds back from how well you've modeled the system, because if you just blindly look at the results, you might be looking at some weird model artifacts that don't actually represent the real world. In terms of tooling, everything's done in Python. We're using this library called Mesa, which is a nice open source library. It's pretty straightforward to use. We found it really effective, very config-led. You get nice modular components, and you get some nice visualization tools that come with it as well. So highly recommend Mesa if you are going around doing agent-based modeling. So what we get once we've done that is we have a tool, a model or simulation tool that a client can use to perform what-if planning. So they can start to think about, what if I increase the capacities? Do I end up getting a bottleneck somewhere down the line? What if I increase the scheduling of this course? Do I get more people through? Or if I reduce the scheduling of the course, does it save me money but still end up with the same amount? And also, they can start to look at long-term impact. So their current capabilities allow them to see very much the here and now, but looking like what the output of training is going to be in 8, 9, 10 years' time, they can't do it. ABM allows them to get some kind of estimate of that. and they can see what the impact of changing the course's scheduling or capacity over time will have on that. And then ultimately, that gives them the ability to strategically plan out their courses, organize all of their training, and also optimize them to meet their objectives that they have around number of people going through and the time they're taking. So with that, I'm going to hand over to Manny, and he's going to talk to you about the more technical parts.
Thank you, James. So, our data science team has built this awesome model, which take a bunch of inputs and run the model, generate the output. But at the moment, it's sitting as code on a Python notebook. So the question is, how do we take this code and build a product out of it, which is user-friendly for our client to use? Right. So one of the first solutions we came up with was something like this. That is, we built an API service which wraps the model, and then we build a front end for that using React. And this way, the client users can log into the website and put in their input parameters, hit the run button, which is going to send a request to the API, which runs the model and respond back with the output, which can be displayed on the website. Right. So that worked really well initially until the complexity of the model increased. We started to notice that the response time was getting into 2 to 3 minutes, which is not a good user experience. So we had to come up with a better way to improve the response time. So we started thinking, instead of real time, what if we pre-compute the output? So we looked at a solution, something like this, where we sort of identify the commonly used input values, and from there we pre-compute the output, run the model and pre-compute the output, and store them on a database. And then from that point, it's easy to, for the user, every time the user comes in, instead of running the whole model, we can just respond from the already pre-computed output on the database. The other benefit with that is, instead of a React application, you could just get away with a simple dashboard. So if you think, if you look at our team, we are a data engineering team, and web development skill is not typically associated with a data engineering team. Whereas building a dashboard is a walk in the park for us, so it simplifies quite well. So with this approach, we were able to bring down the response time to less than 3 seconds, which was really good. Now, the question is, how do we pre-compute? What exactly we should pre-compute? And the approach we've taken here was something like this. For example, in this case, we have 4 input parameters, for example, and each of these input parameters have 3 values each. So if you can think of every possible combination of this, that is 3 to the power of 4, 81 combinations. So we need to make 81 model invocation and pre-compute the output and store it in the database. With this approach, we did our math with what is possible for our clients. In the case, in our case, it wasn't just 4 parameters; it was way more than that. And we did the math; it turned out to be 2 million model invocations. So if you remember, I said it takes about 2 to 3 minutes to do a single model invocation. So if you run it on a container sequentially, it's going to take at least 10 years to complete these invocations. So we need to come up with a better way to do that. We need to run the containers, a lot of containers in parallel, so we can produce output in a timely manner. So we started to think how we can build that solution, and the solution came up. Bad timing. The solution we came up with was to use Airflow. So if you're not familiar with Airflow, it's a data engineering tool used to run workflows. So we came up with a workflow, something like this, where we take a bunch of input values, and from there we generate the input permutations, and then we split that into chunks, and these chunks are split into a number of containers, which runs in parallel and pushes the output into a database. So that's good. The solution works. Now the question is how many containers we need, and we estimate that we need thousands of containers, maybe 1,000, probably 2,000. Where are we going to run it? We need a platform to run these containers. And the answer for that was EKS cluster. So we built the Airflow service on EKS cluster, and that is a full representation of the different components of Airflow service. So if you look at roughly the way it works is a user can submit a job through a web server or CLI or some other way, and it gets written to the database. And there's a scheduler component which sort of pick up that work and then split that into smaller chunks, and these work items are submitted into a queue. And there's a bunch of workers which are waiting for or polling this queue and pick up this work and run to execute the workflow, or in your case, spawn containers on Kubernetes cluster. Right. And so once this was working, the next thing we did was we moved the workplace and containers into a dedicated node group. And the reason for that is, first of all, it gives us a solution. So the cluster we were using was a multi-tenant cluster. The way, if you can imagine, if you're starting thousands of containers suddenly on a cluster, that's going to create a stop on the cluster. And we didn't want to step into other people or cause any disruption on the cluster. Having this separate node gives us good isolation. The other benefit with that is auto-scaling. So in our use case, we have a handful of releases in a month, maybe 2, maybe 3, not more than that. So the rest of the month, we have nothing happening on the cluster, on our service. So having the auto-scaling allows us to scale down to absolute zero, which gives us good cost saving. The other benefit is of having a separate node group is it allows us to define the EC2 instance types we want. So in our case, when we did the model, we built the solution and run it on model. We did a performance profiling, and it turned out that the best spec for us, or the optimum spec for us is 4 GP memory and 1 CPU. That is 4:1 memory to CPU ratio. So having the ability to pick our instance type, we can find the instance type which has this memory to CPU ratio, and this way we can get the best out of the instance type. And lastly, this also allows us to use support instances. So the way the workers work, it spawns containers, and if one of the containers crashes halfway through, Airflow worker just replace it with another container, and it will just resume from where the last one crashed, which is a perfect use case for support instances. So we were able to implement support instances for that as well, which also allowed us to make a lot of cost savings. Once that is done, the next thing we looked at was the Airflow metadata database. And we noticed that has become a bottleneck. So if you were at the previous presentation from Luca, he was mentioning about the DB connections on Postgres, which is kind of the same issue we landed on. So what we did was we replaced the Airflow metadata service, which was initially running as a pod on the Kubernetes cluster, and we replaced it with external RDS server. So what that means is that we can scale up, we can have more connections, and with the dedicated server, it gives us the power to run more workloads, send workloads into it. We use serverless Aurora serverless, which again suited us quite well because we have a variable workload and there's nothing happening. We're able to scale it down to absolute minimum. And when we were running the job, we were able to scale up to, I think, up to 256 ROM on equivalent CPU, which was pretty good. And lastly, the RDS, using RDS means like all the default features that RDS provides, we can benefit from that. Like, for example, the backups, snapshotting, observability, everything was quite useful for us. Some other things we did was in terms of data processing, we were using AWS Athena. So everything from model output is generated until it's pushed into to the dashboard. All the transformations was done on Athena. We were using Parquet for data formatting. We were using table partitioning, and then we used AWS loop crawlers for inference schema. And one of the things we did was, like, every time we release, we have a new release, the schema of the tables were evolving, and using crawlers means that it was automatically picking up the schema evolution and updating the tables accordingly. And the other thing we did was airflow tuning. So ours is not a typical airflow production environment where usually you have a lot of DAGs running and a lot of the energy is spending on scanning for new DAGs, making sure things are running on schedule, whereas in our case, we just have one single DAG running, but it's really big. So we had to tune it in a way that all the energy on that airflow service was spent on running that single job than looking for other jobs which never going to come. And finally, with Tableau, one thing we did was we used a feature on Tableau called data extraction, which basically connects to the live table and download the data and download the data set and stores it locally. And that's how we achieved the 3-second latency even when we were using Athena. With all this put together, so when we did the initial MVP in December, we did 6,000 permutations, and it took us about 3 days to complete the release run. And after that, we worked on all these improvements we discussed today, and with all that together, by June, we were able to run 2 permutations, and we completed that in less than 1 day to release the complete the release job. And this was achieved through running it parallel using more than 2,000 containers on EKS cluster. And that's our story of running millions of simulations on EKS cluster. Thank you.
Questions? Okay, yes, Herbie here.
Thank you, really interesting. You talked about tuning the types of instances being used for the Airflow containers. I was wondering if there was a particular tool or technique used, because that sounds really important in terms of getting the throughput and also keeping the costs under control.
Yeah, so we started with very basic things, as I explained. We looked at the RAM to CPU ratio, and we looked online. There's some websites out there, Vintage, or like we can list from the different instance type and identify the one which matches that ratio. And the other thing we looked at was the spot instances prices, and with this one, which are the ones available. The other really interesting thing was on AWS it publishes the interruption rate for spot instances. We found it quite handy, and we were initially using really large instances like 48x large instances, and then the problem with that is the interruption rate is quite high, and when they go down, that's a lot of containers going down at the same time, causing a lot of interruption. So when we use the instance factor with the lower interruption rate, that reduces it significantly.
Thank you.
Right.
Yep.
Hi there. Out of the 2 million results, how many were viewed?
Sorry, how many?
How many of the results were viewed out of the 2 million results?
We probably don't actually have an exact number of that. The client, if you ask them how many they want, the actual number they initially came up with was 4 billion, I think. So we had to kind of wrest it down to 2 million. It depends on what questions they're going to ask the data. Their goals move over time. So when it comes time to do the strategic planning, they will start to look at them. But I'd say there are a lot that are. Because what we do is basically take the Cartesian product of all of them. But we were trying to be smart about how we would select those and not do the ones that are unrealistic. But in terms of the UI, like Manny mentioned, we're not UI guys, right? We just got a Tableau dashboard with a bunch of filters. So if you start to remove some of those possibilities, then you start to get weird behavior on the dashboard. So that's going to just do more.
Thank you.
Okay, I'll do here.
Just go back to you.
Can I just follow up on the first question? You explained how you went on to scale the containers, but how did you actually beforehand understand what kind of CPU memory usage the containers actually needed?
So we started with the baseline and then started experimenting, going up and down and see the execution time, and also what's the memory usage. And so we kind of tried to stay under the limit, so we're not getting any memory errors. And that.
Okay, so there wasn't an automated tool that you used to do that at all?
Yeah.
There wasn't? Or
there wasn't, sorry?
There wasn't an automated tool to do that?
No, it was really manual.
Okay.
Hi there. I appreciate it's only June 2024, it was the end one. But has the client actually given any feedback to say, yes, it has worked now? We're in September, so it's not a long time, I get that.
Yeah, the timescales we're looking at are in years, so it's hard to say. The initial feedback's good, but they're still trying to assess the impact. I mean, they want us to expand some areas, so that's
a good sign. Thanks.
Hiya, a really cool talk, thanks. How much does that release run cost in the end? 2,000 containers.
It was coming up around, so the single release would be roughly something between 500 to 1,000. Okay.
Cool. Cheers.
Any other questions? Don't be shy. No. I have one. So is there any specific lesson learned that you've had from this that if you could go back to the very beginning and go, I wish we had done that first? Anything comes to mind?
We've been trying at the moment to try and see if we can make the real-time solution better, because like what was mentioned there, you don't know what they're going to want. They're going to want what. So we have challenges sometimes that the actual values that we have given them pre-computed aren't necessarily always exactly what they want, and then maybe they want to just move the needle a little bit. I think more time spent on how we can get a real-time solution working probably would be good value. We have been making good progress there. Who knows?
And you mentioned there were no automation tools. Do you wish you could have sorted that out? How much of a difference would it have made to this if you had some kind of automation
for the tuning
instead of the manual? Yeah.
Yeah, I was watching the previous presentation, which I wished I had that thing before. And so a lot of those things which were used to tune Lambda is also applicable in container world as well. So yeah, it was.
Anybody else? Any questions? Yeah.
How flexible is this, or how easy would it be to remodel that to another query, if you like? Because you would kind of say the customer wants this. So could you reuse that technique?
Yeah, it's not config-led, so you have to define all the values of the pre-compute, like that. They're managed in a table with the parameters and the different values. We basically have that in a JSON file, so you just populate that and then trigger off the release process and wait a few hours.
Would that change your scaling structure depending on the
Depends on the
requirement?
model itself, like the actual. Yeah, so depending on the complexity of the pipeline that's been modeled, the runtime is quite different. So. Pretty fun. So yeah, I mean, we are, like I said, we're expanding into a slightly different area, and the complexity is far less. That hence the kind of real-time solution come in. So yeah, we go down from the 2 to 3 minutes to the 20 to 30 minutes. Start to kind of open up different possibilities there.
Cool, thank you.
Anyone else? Going once, going twice. So you just need to put a little bit of pressure.
Yeah, so you said that you've pre-computed all these. So you've got all these results, and you're giving those to the client. If the client then wants just to make a few small tweaks, do you then have to recompute everything, or how amenable is this to small, subtle changes?
Not the most. A lot of our time is spent working with the client to get those locked down and contractually obliged to not change it too much. But yeah, effectively, the model itself, because you are simulating a large number of agents running through it, and they all have probabilities to take certain actions, it's not deterministic. So each run, you get slightly different results. So we try to, not make too many little changes, but that is a challenge. The way we did it was just engage with the client and way through the development process. So every time we made a small improvement, we did a release, gave it to them, and got their feedback quickly. So if there was any parameters that we missed or anything that they want to see, now they've had a little chance to play with the tool, then we'll incorporate it in the next cycle.
And that was one of the issues with the initial MVP release. It took us 3 days to run the release. And when we released it, we found there was a bug in the code, and we had to rerun it for another 3 days, which is not a good user experience. So that's why we wanted to invest in that scalability, so we bring down the release time as much as small as possible. So if there's an issue, we can quickly iterate it to.
We could scale up even more and bring that down, but it just comes down to cost. We can't just burn money.
Cool. Anyone else? All right.
Hey, since you've got all those results, would you be able to suggest which is the best one, or a number of options to them instead of them having to ask the one they want?
Yeah, we have actually talked about it in the talk, but we've done a little bit of optimization where they'll have some predefined objectives in mind, and then we actually just use the ABM to actually show them what will give them that output. But generally, they kind of feel like they want to have a little bit more control and have them play themselves and answer themselves, because there's a lot of nuances in there that are quite hard to capture.
Yeah, just figured you got that many results, might as well use them.
Yeah, definitely. And we have a team of data scientists who do that kind of work, analyze the outputs.
Cool.